Okay, so 2,7 is transformations of functions. So now we're going to be taking those basic parent functions that we talked about and transforming them, exactly what it sounds like. So we're going to shift it left, right, up, down, reflect it, stretch it, shrink it, all the things, okay? All right, so the first two are at the top of your paper there, and you probably don't need a calculator for these. We'll see. All right, so we're going to take a parent function. So the first one's going to be an x cubed function, and then we're going to do a couple things to the equation and just see how it affects the graph. So x values for x cubed, do I have any restrictions, any numbers I can't plug in? No, so a good set of values you could use on your table is -2 to 2 to start, and then you could always like extend those values one way or the other if you felt like you needed to. So -2 to the third power, what does that give me? -8. -1 to the third power. -1. 0 to the third power. 0. 1 to the third power. 1. 2 to the third power. 8. And then if we're going to graph it, let's see, -2, -8, -1, -1, 0, 0, 1, 1, 2, 8. There's my parent function. Okay. All right, now we're going to transform it. So using those same x values, and this is where you gotta use a little brain power. So we're plugging -2 in for x. Order of operations. -2 plus 2 gives me 0. To the third power is 0. -1 is -1. Okay. Plug in -1. -1 plus 2 is 1. Cubed is still 1. -1, 0. Plug in 0. 0 plus 2 is 2. Cubed, that's 8. -1, 7. Plug in 1. 1 plus 2 is 3. Cubed, that's 27. -1 is 26. I'm not even going to plug in the last one because they're getting too big. All right, so now plotting my x and the y on the far side, so either end of the table. So -2, -1 is going to be the first point I plot. -2, -1. Then -1, 0, then 0, 7, and you can see that's going to be my function. Okay, so now if you were going to compare the purple graph, and you can compare like point to point, kind of like these 2 points you can compare to one another, how did the purple graph move to get to the red graph? How was it shifted? 1, which way?
Left.
A little bit more left. It did go left though. How much left? Left 2. And then if we're going from purple to red, it went down 1. Okay, so from the original function, from the parent function, to the transformed, the new function, we could take all the points and just shift them. Left 2 and down 1, and we end up with the new one. Now, do you see how there's a 2 and a 1 in the equation? So our goal in the lesson today is to kind of be able to figure this out without having to graph it. Just be able to look at the equation and say, I know what that 2 is going to do, and I know what that 1 is going to do to make the equation change. Okay, so let's, why don't you guys try this one with your partner? Okay, same thing, but it's a square root function, so are we plugging negatives in? No, so I would probably use like 0, 1, 4, 9. I mean, could use 16, I guess, if you want to. Numbers that are, easy to do calculations with. All right, go ahead. Give you a few minutes. Let's see what it looks like. All right, so this is what your table looks like. I think that I added another point here. So 4 isn't actually the first number I'm able to plug into that new equation. 3 is, because 3 minus 3 is the square root of 0. And that's really where the equation starts. If you can see that point, I think it makes it a little more obvious that it's been shifted to the right 3 units. Okay, decimals are fine when we're graphing something. We don't have to worry about like exact answers for these. Okay. right, but again, this is kind of tedious, so you'll be graphing on Math Excel a little bit. Remember, when you're graphing on Math Excel, you're going to hit the little, button to the side that is a certain tool, square root tool or a cubic tool or whatever, and then just make sure you follow the instructions really carefully about what kind of points it wants you to plot. Like a cubic function, you're probably going to have to plot 3 points. Any 3 points will work, but make sure you kind of have those in a table ready to go when you get to those problems. All right, so now that's how we would do it if we were just kind of taking the equations and plotting and comparing. Not like the greatest way to answer these questions, though. This stuff you don't need to write down. You can see on your paper, you've got like a summary of this that I'll show you in a second. So in general, things that are added and subtracted in the equation perform shifts to our graph. If something is added or subtracted inside the basic function, so like inside a parentheses or under a square root or inside an absolute value, that's going to shift it left or right. If something is added outside of a square root or an absolute value or a parentheses, that's going to shift it up or down. Okay. Then we talk about reflections. Reflections are, you thinking, Kristen? You can just eat. Like, you can have your snack out and eat it. You don't have to sneak it. I mean, you can. You're okay. All right. All right. Reflections are negatives. So if you have a negative outside of the function, it's going to reflect over the x-axis, which kind of looks like that. Reflection over the y-axis will be a negative inside the function. Reflections and shifts are called rigid transformations because it doesn't change the shape of the graph. It just changes like its orientation or its location, but the shape is still the same. Then we have stretches and shrinks, which are non-rigid transformations because they distort the way the graphs look. I like to think of these like taffy. If I have a vertical stretch or shrink, think about a piece of taffy and I'm pulling it away from the x-axis or I'm pushing it towards the x-axis. So a vertical stretch will look like something gets skinnier because I'm pulling it away from the x-axis, and a vertical shrink will look like it gets kind of fatter, a little wider in the middle because I'm pushing it towards the x-axis. And then you can do the same thing with horizontal stretches and compresses. We can pull away from the y-axis or we can push towards the y-axis. Those are going to be things that are multiplied in our equation. So adding and subtracting are going to shift it in a direction. Multiplying is going to stretch it or shrink it in a direction. Now, the actual rules for all of this are at the bottom of your paper. So it's important to recognize here that the brackets here and here could be any of our basic parent functions. So they might be an absolute value bar. It might be a square root or a cube root. It might be a parentheses that's squared or a parentheses that's cubed, or it might be a fraction, and this does happen in the denominator if it's one of those reciprocal functions from yesterday. So that could be anything. Then we've got our x. What's happening with the x will perform the following transformations. If I have a negative where my x is at, it's a reflection over the y-axis. If I have something that's multiplied where my x is at, that is a horizontal stretch or shrink. And based on what this number is, it tells me if it stretches or shrinks. If this number, and this is a little backwards, but if this number is smaller than 1, it stretches it. And if it's bigger than 1, it shrinks it. So for example, if I had a number in there that was a 1/2, that would actually be a stretch of 2. I would use its reciprocal value. Or if I had a 1/3, it'd be a stretch of 3. Numbers that are added or subtracted on the inside, move it left and right. Again, these are a little bit backwards. It moves to the right if the value is negative. Like if you guys look at that square root problem we did together, it was a minus inside that square root, but it moved it to the right. It's because it's adjusting our x values. And then left is going to be a positive in there. Then A and D are the guys that happen outside of the basic function. So a negative outside will be a reflection over the x-axis. A out front, something that's multiplied, will be a vertical stretch or shrink. These are exactly as you would think. If it's a number bigger than 1, it stretches. Number smaller than 1, it shrinks. And then D, same thing. It shifts up or down. If it's positive, it goes up. If it's negative, go down. The ones in the middle are always, this guy and this guy are always the ones where the most mistakes occur, just because they're kind of backwards of what your intuition would say based on the numbers that you see in the equation. Okay, so put a little asterisk by those. All right. So you're going to use this table for almost every single problem and homework and quizzes and everything. By the way, your quiz on Friday is open notes. You can use this. All right, so we're going to start with these problems. I think these are on the back of your paper, maybe? Or at the bottom? At the bottom? Okay. First one anyway. So it says, for the problems below, describe the transformations that produce the graph of G from the graph of F. So the graph of F, or the function F, is just one of the parent functions that you guys researched, okay? Then G is F that has been transformed. We put some numbers in the equation, and we just want to know, what did those numbers do to the graph without having to graph it? Okay, so I want to first just identify there are 3 things that have changed. Each thing that has changed is going to perform a transformation. So I'm just going to label those. So I have a negative on the outside. We got to figure out what that does. I have a +4 inside, and I have a -3 outside. Okay, so now is where you can use the chart. If I have a negative outside of my basic function, what does it do? Reflect over the x-axis. Good. Okay, if I have a +4 inside, so that's going to be the C value you're going to look at in the chart. Those are things that are added or subtracted inside. What's it going to do? That's if it's multiplied, it would be a horizontal shrink. Yes, but it's added. So shift which way? Left. These ones are backwards, remember. Anything that's inside is backwards. It's going to move it left 4. And if you want to be fancy, you could say horizontal shift left 4, but left 4 is fine for me, okay? And then what about the -3 outside? At the end there, what does that do? Down 3. Okay, so that's all we're doing for these, is we're figuring out what do these numbers do to the equation. And if you wanted to check it, you could graph those two and compare the pictures. All right, flip it over. Let's do the next one together. All right, I've got x cubed, so that's my parent function, and then I have this. Now, actually, I'm going to rewrite this equation before I do anything, okay? I'm going to write equals 1/4. I'm going to keep that there. That negative is not allowed to be next to my x. If you look back at your chart, if I want to use these rules, and you do want to use these rules, if there is anything multiplied by the x, it has been factored out. There is a parenthesis separating it. If there is not a parenthesis separating a number from the x, you need to factor it out first to make it look like this. Okay, so the problem that we're looking at has a negative in front of it, and there is not a parenthesis separating it. So I'm factoring it out. Now, it's still inside the cube, okay? But I'm pulling it away from the x and the 1. So when I factor a negative out, all it does is change sign. We know that. So it's going to be an x minus 1, and you could very quickly mentally just like distribute that negative back in and make sure it's the same as what you started with, plus 2 at the end. Okay, so we always want to make sure it's in that same form to match our table before we use the rules in the table. All right, so now things that are different. The first thing that is different is there is a 1/4. It's outside and it's multiplied. What does it do? It close. Vertical shrink. Yep, and for me, that's fine. Vertical shrink. You could say by 1/4 though. If it's outside, it's going to be exactly what you would think. If it's a number smaller than 1, it's shrinking. If it's a number bigger than 1, it's stretching, and it's vertical if it's outside. Okay, so that's the A value. That 1/4 is the A we're looking at. Now the negative is inside. What does a negative inside do? Reflect over the y-axis. Okay, what does the -1 on the inside do? Be careful, anything on the inside's backwards. Right 1. And then the plus 2 at the end does what? Up 2. Okay. With your partner, somebody near you, I want you guys to do the bottom one. Is the bottom one in the right form? No, there's something multiplied by the x, so you need to factor it out before you can use your rules. All right, go ahead. I'll give you a few minutes. Let's check it. Oop, there it is. All right, so you factor the 3 out. It's still inside the absolute value bars, but if I divide 3 into both those terms, I get x minus 2 that's left. The 5's on the outside, so it is a vertical stretch by 5. The 3 is on the inside. Remember, anything on the inside is backwards. Okay, so it's a horizontal shrink by 1/3 because it's a number bigger than 1. We always use the reciprocal for those horizontal ones. And then the minus 2 moves it right to. That last answer is the one you would get incorrect if you forgot to factor your number out. If you didn't factor your number out, you'd say it was right 6, which is incorrect.
So why is it incorrect?
Because we use reciprocal values for those horizontal numbers. Whatever b is, the reciprocal of that is actually what's happening to the graph, horizontal stretch or shrink. So if I had if I had 1/3 in there, my answer would be a horizontal stretch by 3. Flip it. Okay. It's only that b value, the number in front of the x, you have to worry about that. Just a rule we got to remember. Okay. Other questions? That. Okay, now next slide is not on your paper. You don't have to write anything down. I just want to talk about a couple things. These can sometimes be tricky about what is inside and what's outside. If you look at the bottom two, these ones are tricky. So here we have an exponential function. When we say something is inside the function in an exponential function, it's in the exponent itself. It's where the x is at. That's what you want to remember. Inside is where the x is at. So like that +4 up there is a +4 inside the function. So that would move it left 4. Everything else is as normal. The 3 would be a vertical stretch, the negative reflection over the x-axis, the +2 up 2. Okay. Then we have the reciprocal ones, which I think are the hardest ones to see, where the x or the x squared is in the denominator, where a couple of bars. That means anything in the denominator is inside the function. Okay, again, it's wherever the x is at. So that +1 there would move it left 1. But that -3 and that 5 are outside of the function. I could even rewrite this as -3 times 1 over x plus 1 plus 5. I could kind of separate the numerator out of there, so that might make it a little easier to see how you can compare it to the original function. But just be careful with those because they can look a little tricky. Rules are the same, you just got to know where to look. Okay, next. We're going to do these problems backwards now. So now I'm giving you a basic function, a parent function. I'm giving you the transformations, and your job is to write the equation to make those transformations happen. So the first one is f of x equals square root x. So when I do these, I just do them all in one step. I just set up a big square root with an x, and then I put numbers wherever I need to make transformations happen, okay? So the first thing I need to do is move it 2 units down. So what do I need to put where to make sure this guy goes 2 units down? 2 where? Outside or inside? Outside, added or subtracted? Subtracted. -2 at the end will move it down 2. Good. Reflected over the x-axis. Well, reflections are negatives, so you just have to worry about, does the negative go inside or outside if it's over the x-axis? Outside. Okay. And then compress or shrink. It's another word we'll see. Shrink. Vertically by a factor of 1/2. If it's a vertical stretch or shrink, is that outside or inside? Outside, and it's exactly as we would think. 1/2. Okay. Again, the horizontal ones on the inside are the ones where you're going to flip it and use the reciprocal. All right. You guys try the 2 below. All right, let's check our answers. You got to be real careful when you set these up with parentheses. A negative or a vertical or a horizontal stretch or shrink are going to be outside the parentheses where the x is at. And then you can, Like here I distributed my negative in, or here I distributed my 3 in. So I think Math Excel might have you distribute the number in. But either answer for me on a test or a quiz would be sufficient.
So those would be parentheses, not brackets on here?
A parentheses and a bracket are the same thing. So if you have brackets, that's fine. Sometimes we'll do one of each just to like distinguish which set is which, but it does not matter. Okay, be careful with that compression horizontally. It's reciprocal. It is 3. Questions do you have on those? Anything? Writing the equation? No? Okay. Moving on. We just got a couple more things. All right. The next thing is on your paper. So let's say, this is worst case scenario, you do not have an equation that you can just look at and say, here's what transformations have occurred, or an equation where you can plug numbers in to create the graph. You just have like this set of points, like a piecewise function, kind of. And we have to perform our own transformations to it. So physically, we are going to move the points ourselves. We're going to push them or pull them away from an axis, or we're going to reflect them, or we're going to move them up, down, left, right, if we don't have an equation. If you have to do transformations on your own by hand with no equation, there is an order. So think of this kind of like an order of operations for transformations if you are performing them. The first thing you do is a horizontal shift, and they go in this order because these are the things that start closest to your x value if you were to plug something in. The thing that's closest to my x value is the left-right shift, so that's what happens first. Then any stretches or compresses, things that are multiplied, and actually those and the reflections really do occur at the same time. We write them separately, but they can occur at the same time. And then the last thing that happens to our x value after we plug it in is we add or subtract that number at the end, which shifts it up or down. So you can kind of see the progression if you were to look at like our chart to see how things are, how close something is to our x. That's where this is coming from. All right, so what we're going to do is we're going to take that function and we're going to transform it. And you need to be able to look at the notation and kind of read it. So f of x is our original function, and there's things that have happened to it. There's a 1/2 on the outside and a +1 on the outside. What does a 1/2 multiplied on the outside do? Shrink how? It's a vertical shrink by 1/2, okay? And then the +1 does what at the end? Up 1. So that's all you need to get from that notation. You need to be able to look at that and say, okay, it's been shrunk by 1/2 and it's been moved up 1. Now, as far as the order at the top goes, there are no horizontal shifts left or right. So the first thing that's going to happen is the vertical shrink. So vertical shrink, remember our taffy, we're going to make it shorter vertically, okay? And then up 1 is going to happen second. So the first thing I'm going to do is I am just going to plot those original points on here. Okay, so, and you guys can estimate the best you can. I know those axes didn't print out super well. So there's -5, -3, -1, -1, 1, 3, and 4, -2. There's the original graph of f of x, or g of x. No, f of x. That's my f of x. We're okay. All right. Then we're going to do a vertical shrink. Okay, so vertical shrink, vertical is up and down, shrink it shorter, okay? So what we're going to do is we're going to take each point. So I'm going to start with, and I'll just go up to the board and talk about it here. So I'm going to start with this point, and we are pushing 1/2 of the distance to the x-axis vertically, up and down. Okay, so like this point is how far from the x-axis right now? 2. So 1/2 that distance is 1. That's where that point moves to. It moves to 1 unit away. It's getting shorter, okay? This point is how far from the x-axis? 3. 1/2 of that distance is 1.5. Push it towards the axis. Okay. This point is 1 unit away. Push it towards the x-axis, half the distance. It's going to be right below the axis. And then this guy is 3 units away. Push it half the distance. It's going to be 1.5. And then if you connect those dots, do you guys see how it shrunk vertically? Okay, so that purple one now is 1/2 times the original function, f of x. Okay, so I did that first part. The only thing I have to do now is take all of my points and move them up 1, and that's easy. You literally just move each point up 1 unit, and that's going to be our answer. So up 1, we're looking at the purple graph, moving it up 1, up 1, up 1, and then that last guy is going to end up on the x-axis. So if you have a lot of transformations, these can sometimes get a little messy as far as like the work goes, but that last graph, the black one, is the answer. That's the original function after we shrunk it by 1/2 and shifted it up 1. Now, if you were going to stretch, like let's say it was a vertical stretch by 2, you just double the distance from the axis. So if I was like 3 units away, I would make it 6, and I would go further away. So that's what makes it taller instead of shorter. Okay. One more. G of x equals f of 2x minus 2. First of all, I'm not allowed to have a number next to my x, so I'm going to factor it out. 2, and that'll make it an x minus 1 in there. Okay. The 2 does something, and the 1 does something. What does the 2 do? If it's multiplied, it's on the inside. Horizontal close. Horizontal shrink by how much? 1/2. We use a reciprocal for those ones. Those are the only ones that are weird. And then the minus 1 on the inside is going to do what? Oh, and actually, I shouldn't put those there because actually that one's going to happen first. It's going to move it right 1. Okay, and that's actually the guy that's going to happen first because my shift, horizontal shift left and right is going to happen first. And then any stretches or shrinks happen second. All right, so again, I'm going to start by just graphing my original points. -5, -3, -1, -1, 1, 3, 4, -2. Original points, f of x. Okay. The first thing that I need to do, according to my little order of operations here, is just move everything to the right 1 unit. That's easy enough. To the right, to the right, to the right, to the right. Okay, so that is f of x minus 1. Okay. The last thing I need to do is a horizontal shrink by 1/2. So horizontal is left, right. Shrinking it is making it skinnier. Stretching it is making it wider. Okay, so this time if I want to make it skinnier, horizontal shrink, I'm pushing it towards the y-axis instead of the x-axis is the only difference. Again, still half the distance. That's what that 1/2 tells me. So this point, this first purple one on the bottom there, is 5 units away from my axis. I want to push it half the distance, so I'm going to move it to 2.5. Okay, oh, that's that one. Just kidding. Here we go. Okay. The one at the top of the peak there is 2 units away. It's actually just going to go right back where it started. Half the distance. If you're on an axis, how far from the axis are you? 0. And what's half of 0? Is it going to change? No. It's on the axis. It's going to stay on the axis. And then the last one, let's see, the purple one at the bottom there is 4 units away, half the distance, 2. And you should be able to see these transformations. You should see the compression, the horizontal shrink. So that's f of 2x minus 1. Now I did that horizontal shrink by 1/2. And that is the original function there. Okay, so these are the toughest ones because you physically have to move all the points and it's a little tedious. All right, that's everything on your paper. Now, you don't have to write anything down, but I want to give you a hint for Math Excel. We're just going to talk about this problem real quick. So you're going to see a problem that looks just like this. I promise you it's going to look complicated, but it is very easy. So I have a graph that has x-intercepts at -4 and 2. It could literally be anything, but I'm going to make my life easy and say it is a parabola. -4, 2. Okay? So I want to know what are the x-intercepts going to be if I put a plus 5 in that function. What does a plus 5 do inside the function? Left 5. So if those are my x-intercepts and the whole graph is moved left 5, what are the new x-intercepts going to be? It's going to be -9 and -3. That's it. That's all you have to do. Okay? What if there's a -3? What does it do? Right? 3. Okay, so if I take my x-intercepts and I move them right 3, where are they going to end up at? -1 and 5. What if I put a negative outside the function? What does that do? Reflect over x-axis. So if I take that graph and I flip it upside down over the x-axis, are those x-intercepts going to change? They are not. Still going to look the same. What if I reflect over the y-axis? That's what a negative on the inside does. So if I take my graph and I flip it this way, is it going to change my x-intercepts? Yes, it is. What's going to change them to? They're going to be opposite. It's going to be a +4 and a -2. What does that 15 outside do? Vertical stretch by 15. Now, that means we would take a point and we would pull it 15 times its distance away from the x-axis. I would make it taller. But we only care right now about the x-intercepts, which are currently 0 units from the x-axis. So are they going to change if I stretch the graph? They are not. Doesn't matter what that number is. They're going to be the same. Now, would they change if I did a horizontal stretch or shrink? Yeah, they'd get closer or further away. All right, that's it. So we did all of 2-7 today, which means you have earned yourself a Math Excel workday tomorrow. Yay. All right, so Math Excel workday tomorrow, and then Friday is open note individual quiz over 2-4 to 2-7. So open note includes all of those handouts that we have been using. I would make sure I have those on Friday, and I would make sure I've got some Math Excel practice so you're ready to go. Yeah. The test will not be open note. So this chart you will eventually need to memorize. Absolutely. Yeah. Good try, though, Steph. Good question. All right. Cell phone lotto. I got 19. Nobody. Let me grab your phone. When's the 2-7 Math Excel due? Monday? That sounds right, I feel like. Oh yeah, Monday. I can probably get that class tomorrow. Oh yeah, sometimes it gets stuck. Hold on, I'll help you.